I said in the last video that propositional inference is probably not tractable. It's probably not possible to write a computer program that is guaranteed to be able to prove any propositional theorem from any knowledge base in a reasonable or non-exponential amount of time. So there are sort of two ways we might confront that issue. One way is that we might accept it and just make the most efficient inference algorithm that we can and hope that lots of theorems will be efficiently provable and that the theorems that really give us trouble and cause exponential time delays for our algorithm are going to be rare. And that approach is taken pretty frequently. So there's some very powerful general purpose theorem provers out there that actually can deal with lots and lots of large inference problems efficiently, but they can't provide that guarantee, right? They can't say that they'll always be able to efficiently give an answer. So the alternative is to restrict the problem a little bit. So reduce the class of possible axioms that will allow into our knowledge base so that we can make some guarantees about the efficiency of inference. And that's the approach that we're going to talk about now. And that brings us to propositional definite clauses. And I want to point out here that our authors are a little bit sneaky. So you won't really find this issue that I just brought up addressed here. They introduce propositional definite clauses, and then from that point onward, they just restrict all of their inference procedures to working in this domain. So a little bit sneaky, but that's okay. So what is a propositional definite clause? It's either an atom, so the same kinds of atoms that we saw before qualify as definite clauses, or it's of the form A if B, where B is either an atom or it's a conjunction of atoms. So here are some examples of things that are not definite clauses. Apple is eaten and bird eats apple, right? This isn't in the form of that we require. It's a conjunction, but there's no if. This one looks like it should be, but he's pointing out that these are syntactically incorrect atoms because they don't have because they have capital letters. So this is a nice, typical, beautiful-looking definite clause. It's got an atom on the left, and on the right, it's got some conjunction. So this is limiting. There are logical statements that can't be put in this form, but you can say a lot in propositional definite clauses, right? So in fact, you can build whole programming languages around this. So if any of you have experience with Prolog, so this is related to the kinds of statements that you can make in a Prolog program. And the reason that we might want to make this restriction is, as I mentioned before, it allows us to do efficient inference. So the textbook outlines a couple of different proof procedures that can be, and they're both efficient, given that we have a knowledge base that's a set of definite clauses. The bottom-up proof procedure, and I don't think I want to go through this in detail, but the idea is pretty straightforward. We just we start with an empty set of clauses, an empty set of atoms that have been proven, and then we just keep adding atoms to that set as we are able to by proving the right-hand side of those clauses, right? So probably the easiest thing would just be to think through this example a little bit. Here's the knowledge base. This algorithm starts always with this empty set of proven clauses, and then it starts just working through the knowledge base, looking for axioms here that allow us to prove a particular atom. And in this case, right, D and E follow pretty easily, so D goes in, E goes in. And then once we have D and E, it's going to allow us to, right, for example, once E is in there, we can conclude C. So C will be the next one that will end up in there. And once we have C, E, and D, right, we can get B from D and E. So B will go in there. What's the last one that goes in? A. So we can, once we have B and C, we can conclude A. And so we just keep working our way through our set of axioms and stuffing atoms into this proven set as we go. So this is, I won't read through all of this, but this procedure is sound. It only draws valid conclusions. It's efficient. It's guaranteed to be run in time linear with the size of the knowledge base, and it's complete. It's going to prove any of the atoms that are actually provable. So that's pretty good. They also describe this top-down proof procedure, which basically just works in the other direction. So rather than building up every possible atom that can be proven, we start from a particular answer that we want to get. We start by, for example, asking if this conjunction is true, and this gives us a set of goals, and then we work backwards, or work top-down, through our set of clauses, trying to prove all of the atoms in that conjunction. Right, so we start out, we want to know, is A true? So we look through here and we find that A is on the left side of this clause, so that gives us a new set of goals. We want to now show B and C, right? That's what's happening here. And so then we start working on B, and we work our way through here to find B on the left-hand side, and we find, yep, okay, there's a B on the left-hand side with a D and E on the right, and we add that now to our set of things we have to prove. Now we have to prove D and E and C, and that'll give us, right, so that's equivalent to proving, right, this is now equivalent to proving this, and we keep going. Eventually we get to the point where we need to prove that E is true in order to show that A was true, that we were originally right. We find the E in there and we're done, so we can conclude that A was true. The nice thing about this, right, so which is better, top-down or bottom-up? The nice thing about top-down is that we only involve axioms from our knowledge base that are actually relevant to the conclusion that we're trying to reach. So bottom-up just sort of mindlessly builds a set of things that we can prove, and then we look at all the things that we did prove to see if what we wanted to prove is true. Top-down starts from the goal that we actually want, so if there are a lot of axioms that don't really have anything to do with the proof that we're trying to construct, they won't necessarily get involved, they won't necessarily get in the way, so this can be more efficient. This is kind of nice. This is showing an example of working through one of those proofs, and it's one of the things that's pointed out here is that when it's time to take a step in one of these proofs, we often have some choices available to us. So that becomes kind of a graph search algorithm where, right, here are 3 possible steps that we could take from this point in the proof. If this is the knowledge base, we're trying to prove that A and D are true. So we could, I imagine there's an H implies A in here somewhere, right there. So that's one possible step we could take in the proof. There's an A if G in here, right there. So that's another avenue we could be taking in the proof. It looks like there's also an A if B and C in here, and that's another step that we could take in the proof. So we could do, right, who knows what path we're taking through here, but this is the actual sort of search tree that comes from this top-down search mechanism. And you can imagine doing any of our graph search algorithms to complete this proof. And as long as our search algorithm is complete, then this inference procedure will be complete.